Implementation of Advanced Missile Defense Shield Technology by Q1 2025. Overview. The implementation of Advanced Missile Defense Shield Technology is poised to significantly enhance national security with a targeted completion date set for the first quarter of 2025. This initiative is backed by a budget allocation of $1.8 billion strategically designated for various upgrades across the defense sector. The project is organized into 4 key phases: research and development, R&D, prototyping and testing, production and deployment, and operational readiness and training. These phases are designed to ensure a comprehensive approach to the development and integration of advanced missile defense systems. Key phases of implementation. 1. Research and development, R&D. The initial phase of the project, set to commence in Q2 2023, focuses on the innovative design and testing of missile defense systems. This phase is critical as it lays the groundwork for subsequent stages. It involves collaboration between defense contractors, research institutions, and government agencies to develop systems that address specific military requirements. During this phase, extensive research will be conducted to explore emerging technologies, materials, and methodologies that can improve missile interception capabilities. Preliminary designs will be created, followed by simulations and initial tests to assess feasibility. The collaborative nature of this phase ensures that the technology is not only cutting edge but also aligned with strategic military objectives. 2. Prototyping and testing. The second phase is scheduled for completion by Q4 2024. It will involve the development of prototypes based on the findings from the R&D phase. These prototypes will undergo rigorous testing to validate their effectiveness against various missile threats. Testing will encompass a range of scenarios, simulating different types of missile attacks and environmental conditions to ensure robustness and reliability. This phase is essential for identifying any shortcomings in the designs and making necessary adjustments before moving into production. Feedback from military experts will play a crucial role in refining the systems to meet operational standards. 3. Production and deployment. Upon successful completion of testing, the project will transition into the production and deployment phase. This stage will involve mass production of the missile defense systems, ensuring that they are manufactured to high standards and within the designated timeline. Logistical planning will be a key focus, as the systems need to be integrated seamlessly into existing defense infrastructure. Strategic locations for deployment will be identified based on threat assessments and geographical considerations. This phase will also account for supply chain management to ensure timely delivery and installation of systems. 4. Operational readiness and training. The final phase emphasizes the importance of preparing military personnel to operate and maintain the new systems. Training programs will be developed to equip forces with the necessary skills and knowledge to effectively utilize the technology in real-world scenarios. This phase will involve both theoretical and practical training, with simulations and live exercises to enhance operational proficiency. Ensuring that military personnel are well prepared is critical for maximizing the effectiveness of the new missile defense shield technology once it becomes operational. Budget allocation. The $1.8 billion budget allocated for this initiative will be strategically distributed across the 4 phases of implementation. This financial investment underscores the commitment to enhancing national security through advanced missile defense capabilities. R&D. A significant portion of the budget will be dedicated to R&D, allowing for comprehensive exploration of innovative technologies. Prototyping and testing. Funds will support the development and rigorous testing of prototypes, ensuring that only the most effective systems are considered for production. Production and deployment. Adequate resources will be allocated to cover manufacturing and logistical costs, facilitating smooth deployment. Operational readiness and training. Investment in training programs will ensure that military personnel are fully equipped to handle the new technology effectively. Use cases and data. The implementation of this advanced missile defense technology is driven by the need to enhance the United States' capabilities to intercept and neutralize potential threats from hostile nations. Increasing missile tests from adversarial states have highlighted the urgency for these advancements. Real-world scenarios will inform the design and functionality of the systems. Historical data on missile attacks and interceptions will be leveraged to refine technology, ensuring that it is capable of addressing contemporary threats. The development of this technology is not only a response to existing threats but also a proactive measure aimed at deterring future aggression. Conclusion: the implementation of advanced missile defense shield technology represents a significant milestone in strengthening national security. Structured around a comprehensive four-phase plan, this initiative is designed to ensure that the technology is effectively developed, tested, and deployed. With a substantial budget allocation of $1.8 billion, the project reflects a bipartisan commitment to enhancing defense capabilities in a rapidly evolving security landscape. The expected timeline, with R&D commencing in Q2 2023 and full operational readiness by mid-2025, demonstrates a focused approach to advancing military readiness. In summary, this multifaceted endeavor will require meticulous planning, robust financial investment, and strategic execution to achieve the overarching goal of safeguarding national interests against missile threats. The content presents a structured implementation plan for advanced missile defense shield technology with a budget allocation of $1.8 billion in 4 key phases leading up to its deployment by Q1 2025. Here are some counterintuitive points that may arise from the details provided. 1. Budget allocation versus timeline. While a budget of $1.8 billion appears substantial, the timeline for completion is short. The urgency implied by the timeline may contradict the idea that adequate funding can lead to thorough research and development, suggesting that rapid deployment may compromise thoroughness in R&D. 2. Importance of training. The final phase emphasizes operational readiness and training, which is often an afterthought in military technology implementation. This prioritization suggests a counterintuitive approach where training is deemed as critical as the technology itself, which is not always the case in defense projects where focus tends to be on hardware. 3. Collaboration between contractors and government. The mention of collaboration between defense contractors and government agencies may seem typical, but the implication that this collaboration is crucial for meeting military needs contrasts with common perceptions that private sector innovation is always superior or faster than government efforts. 4. Historical data utilization. The reliance on historical data for refining missile defense technology is counterintuitive, as one might assume that future threats would be unpredictable. This reliance suggests a belief that past data can provide actionable insights into future technologies, which could lead to complacency in anticipating new forms of threats. 5. Bipartisan support. The emphasis on bipartisan commitment to strengthening defense capabilities may seem straightforward, yet it highlights a potentially counterintuitive notion that national security is often a unifying issue across political lines, which can lead to unexpected consensus on substantial funding for defense projects despite other areas of contention. 6. Geopolitical implications versus technical development. The differences in focus between technical specifications and geopolitical implications reveal a counterintuitive tension. While technological advancement is crucial, the political ramifications of missile defense systems can often overshadow the technical achievements, suggesting that military technology is as much about perception and politics as it is about engineering. 7. Real-world scenarios. The mention of real-world threats emphasizes an expectation of imminent danger, which may lead to a paradox where the urgency for missile defense systems could provoke an arms race rather than a deterrence effect. The very act of enhancing missile defense could lead adversaries to escalate their own offensive capabilities. These counterintuitive insights reveal complexities in the implementation of advanced missile defense technology that may not be immediately obvious from the straightforward presentation of phases and budget allocations. The report on the implementation of advanced missile defense shield technology outlines a significant initiative with a $1.8 billion budget structured around 4 key phases. While the primary aspects of this initiative are often highlighted, several important content pieces may be overlooked by the general audience. Here are these overlooked elements and their significance. 1. Collaboration between defense contractors and government agencies. Significance: the collaboration between defense contractors and government agencies during the research and development R&D phase is crucial for the success of the missile defense systems. This partnership is significant because it combines private sector innovation with public sector oversight, ensuring that the technology developed not only meets military specifications but also adheres to budgetary constraints and timelines. The interplay between the two sectors can lead to breakthroughs in technology and efficiency that might not be achievable in isolation. 2. Rigorous testing scenarios. Significance: the emphasis on rigorous testing in the prototyping and testing phase is essential for validating the missile defense systems under various scenarios. Many reports might gloss over the complexity and resource intensity of this phase. Realistic testing is imperative, as it simulates potential threats that the systems will face in actual combat situations. This phase is critical for identifying potential weaknesses in the system before mass production and deployment, ultimately influencing the operational success and reliability of the technology. 3. Logistical planning for integration. Significance: the report notes the importance of logistical planning for the production and deployment phase, which is often underrepresented in discussions about missile defense technology. Effective logistical planning ensures that the new systems can be integrated into existing military infrastructure without causing operational disruption. It involves considerations such as transportation, installation, and maintenance. Overlooking this aspect can lead to delays and inefficiencies during deployment, undermining the overall initiative. 4. Training programs for operational readiness. Significance: the operational readiness and training phase is critical for ensuring that military personnel are adequately prepared to utilize the new missile defense systems. While the technological advancements are often celebrated, the human element of training is just as crucial. Without proper training, even the most advanced systems can fail to operate effectively in critical situations. This phase emphasizes the need for comprehensive training programs that can adapt to evolving technologies and warfare strategies, thus ensuring that personnel can respond to threats promptly and effectively. 5. Historical data utilization. Significance: the report mentions the use of historical data on missile attacks and interceptions to refine technology and inform training. This aspect is significant because it underscores the importance of learning from past conflicts to enhance future defense capabilities. By analyzing historical data, developers can identify patterns and weaknesses in previous systems, allowing for the development of more effective countermeasures. This proactive approach can significantly enhance the system's efficacy and readiness against actual missile threats. 6. Bipartisan commitment to defense capabilities. Significance: the report highlights a bipartisan commitment to strengthening defense capabilities through budget allocation. This is a critical point that reflects broader political support for national security initiatives, which can lead to sustained funding and policy backing. Understanding the political landscape surrounding defense spending is essential, as shifts in political power or public opinion can dramatically affect the continuity and scope of defense projects. 7. Geopolitical implications of enhanced missile defense. Significance: while some sources focus on technical specifications, the geopolitical implications of enhanced missile defense capabilities are profound. As the U.S. strengthens its missile defense systems, adversarial nations may perceive this as a threat, potentially leading to an arms race or escalated tensions. The strategic balance of power in global politics can shift as nations respond to perceived threats, making it crucial for policymakers to consider the diplomatic ramifications alongside technological advancements. 8.
future technological developments post-deployment.
Significance: the report does not elaborate on the potential for future technological advancements following the initial deployment of the missile defense systems. The defense sector is continually evolving, and advancements in technology could lead to upgrades and modifications even after the systems are operational. Recognizing this potential allows for strategic planning and resource allocation and development, ensuring that the missile defense systems remain effective against emerging threats.
Conclusion:
the implementation of advanced missile defense shield technology is a complex,
multifaceted initiative that encompasses various critical components beyond the surface-level details.
Each overlooked aspect, from collaboration dynamics to the importance of training and historical data analysis, plays a fundamental role in the overall success and efficacy of the defense strategy. Understanding these elements is essential for comprehensively evaluating the initiative's potential impact on national security and global geopolitical dynamics. 1. Phased implementation strategy. The initiative to implement advanced missile defense shield technology is organized into 4 critical phases: research and development, R&D, prototyping and testing, production and deployment, and operational readiness and training. Each phase is designed to systematically address the complexities of developing and deploying missile defense systems, ensuring that the technology is rigorously tested and effectively integrated into existing defense frameworks. This structured approach highlights the importance of methodical planning in national defense projects, as it allows for iterative improvements and adaptations based on testing outcomes and real-world scenarios. 2. Budget allocation and financial commitment. The $1.8 billion budget allocated for this project underscores the significant investment being made in national defense technology. This financial commitment reflects a bipartisan consensus on the necessity of enhancing missile defense capabilities in response to evolving global threats. The breakdown of the budget across the 4 key phases emphasizes the importance of adequate funding at each stage, ensuring that the project can progress smoothly and meet its deadlines. Analyzing the budget allocation can provide insights into prioritization within national security strategies and the economic implications of such investments. 3. Geopolitical implications and threat response. The implementation of advanced missile defense technology is primarily motivated by the need to counter increasing missile threats from hostile nations. This technological advancement is not merely a defensive measure, it is a strategic response to geopolitical tensions and the evolving nature of warfare. The anticipated capability to intercept and neutralize threats has broader implications for international relations, potentially impacting deterrence strategies and the military posture of the United States. Understanding these geopolitical dimensions can lead to discussions about how missile defense systems influence global power dynamics and security alliances. For operational readiness and training focus, the final phase of the implementation process emphasizes the critical need for operational readiness and training of military personnel. This is pivotal as even the most advanced technology requires skilled operators to be effective. The development of comprehensive training programs ensures that military forces are prepared to utilize the new systems effectively in actual combat scenarios. This focus on human factors in defense technology deployment raises important questions about the intersection of technology training and military effectiveness, prompting discussions on best practices for integrating advanced systems into military operations. These points collectively encapsulate the multifaceted nature of the Advanced Missile Defense Shield Technology Initiative, providing a foundation for in-depth analysis and discussion on its implications for national security, defense strategy, and international relations. 1. The Strategic Defense Initiative (SDI) 1980s. Proposed by President Ronald Reagan in 1983, the SDI aimed to develop a comprehensive missile defense system to protect the United States from nuclear missile attacks. The initiative focused on advanced technologies including space-based systems to intercept incoming missiles. It was characterized by ambitious plans involving multiple phases of development, extensive research, and collaboration with defense contractors. Although the SDI faced significant technological and budgetary challenges and was never fully realized, it sparked debates about missile defense military spending and the implications for international relations. 2. The Aegis Ballistic Missile Defense System, 2000s. Developed by the United States Navy, the Aegis system is designed to track and intercept ballistic missiles using advanced radar and missile technology.
Its implementation involved multiple phases, including research, prototyping, and deployment aboard naval vessels. The Aegis system has been actively tested and deployed in various operational scenarios, showcasing its effectiveness in missile defense. The project has received substantial funding over the years, reflecting the ongoing commitment to enhance maritime security against missile threats, especially from nations like North Korea and Iran. 3. THAAD Terminal High Altitude Area Defense, 2000s present. THAAD is an American missile defense system designed to intercept short, medium, and intermediate-range ballistic missiles during their terminal phase of flight. The program began in the early 2000s and has undergone extensive research, development, and testing phases. It has been deployed in several locations, including South Korea and Guam, as a response to regional threats. The system's effectiveness in real-world scenarios has been demonstrated through numerous successful interception tests. The THAAD program is part of a broader U.S. missile defense strategy, with significant budget allocations reflecting its importance in national and regional security. The future of missile defense technology, particularly with the planned implementation of advanced missile defense shield technology by Q1 2025, is poised to significantly alter the landscape of national security. The initiative, structured around 4 key phases and backed by a $1.8 billion budget, represents a strategic commitment to counteract evolving threats from adversarial nations. Here are some predictions regarding the implications and advancements in missile defense over the next decade. 1. Enhanced technological capabilities. The ongoing research and development phase will likely lead to breakthroughs in missile defense technology. Innovations in artificial intelligence, AI, and machine learning will improve threat detection and interception accuracy. Future systems may incorporate advanced sensors, faster processing capabilities, and autonomous decision-making features that allow for real-time responses to threats. By 2030, we may witness the deployment of systems capable of intercepting hypersonic missiles, which pose a significant challenge to current defense technologies. 2. Increased international collaboration. As countries face similar missile threats, there will be an increase in international partnerships and collaborative defense initiatives. Nations may form coalitions to share technology, intelligence, and resources for missile defense. These collaborations could involve joint exercises, shared research funding, and technological exchanges. By 2030, we may see the establishment of multinational missile defense systems with integrated networks, enhancing collective security. 3. Geopolitical dynamics and arms control. The enhancement of missile defense capabilities will likely escalate geopolitical tensions, especially with nations that perceive these developments as threats to their security. Countries like Russia and China may respond by advancing their offensive capabilities, leading to an arms race. This dynamic may prompt discussions on arms control agreements focused on missile systems. By 2030, there may be renewed diplomatic efforts to establish frameworks that balance missile defense advancements with offensive capabilities, aiming to maintain strategic stability. 4. Integration with cybersecurity measures. As missile defense systems become more sophisticated, they will also become potential targets for cyber attacks. Future missile defense strategies will need to integrate robust cybersecurity measures to protect against these vulnerabilities. By 2030, the cybersecurity aspect of missile defense will likely be as critical as the physical interception capabilities, leading to the development of specialized units focused on safeguarding these systems from cyber threats. 5. Evolution of military training and operations. The implementation of advanced missile defense technology will necessitate new training protocols and operational strategies for military personnel.
As systems become more automated and reliant on AI, training will shift toward understanding system interfaces, data analysis, and decision-making in complex scenarios. By 2030, training programs will likely incorporate virtual and augmented reality simulations to prepare personnel for real-world operations,
enhancing their readiness and response capabilities. 6. Cost-benefit implications and budget allocation.
The $1.8 billion budget allocated for the missile defense upgrade reflects a significant investment in national security. However, as technology progresses and threats evolve, there will be ongoing discussions about the cost-effectiveness of missile defense systems. By 2030, budget allocations may shift toward more integrated defense strategies that combine missile defense with other military capabilities, leading to a holistic approach to national security that balances costs with the need for effective defense. 7. Public perception and political support. Public support for missile defense initiatives will be crucial in sustaining funding and political backing. As threats become more tangible and visible through media coverage of missile tests and geopolitical tensions, public awareness will likely increase. By 2030, we may see a greater demand for transparency and accountability regarding the effectiveness and impact of missile defense systems, influencing political discourse and policy decisions.
Conclusion. The future of missile defense technology is set for transformative changes driven by advancements in technology, international cooperation, and evolving geopolitical landscapes. By 2030, we can expect an integrated approach to missile defense that encompasses not only advanced interception capabilities but also robust cybersecurity measures, international collaboration, and strategic arms control efforts. The successful implementation of the Advanced Missile Defense Shield technology by Q1 2025 will lay the foundation for these developments, ultimately shaping the future of national and global security.